Good morning everyone, and it's a great pleasure to be here at the start of what sounds like a really exciting meeting. Really looking forward to the rest of it, less than the next hour perhaps, of my own talking. So my task is to, in the next hour, cover the physics of MRI and magnetism, which is a fairly daunting prospect, but I'm hoping to get to the point where I'll be able to explain the way in which images like these are actually generated. So images which might be weighted to show the variation of particular parameters that we use in MRI, or images that might be slightly more quantitative and cover parameters that perhaps extend outside MRI as well. So I'm hoping to cover nuclear magnetic resonance, NMR, which is the phenomenon which underlies MRI, then to say a bit about how MRI actually works, how images are generated, and to talk about perhaps some of the limitations of MRI and some of the benefits of it, some of its good features, and then to talk a bit about quantitative MRI, and also then to say a bit about the basics of magnetism, and then try to bring the two parts together in looking at how the magnetic properties of tissues affect magnetic resonance images, and hopefully that links into particularly the effects of iron and myelin. So obviously in trying to do this, there are many treatises, if that's the right way of saying it, on magnetism and MRI, and I've tried to hopefully steer a middle course between being too simple and being too complex. So half is very complex and half is very simple, so perfectly balanced presentation. But I've tried to keep a middle course, so I hope I managed to do that. But occasionally I will, for the MR experts in the audience, I have sort of simplified things occasionally, so I hope you'll let me get away with that in this context. Okay, so NMR. NMR is a phenomenon of nuclear magnetism, and you probably know many nuclei do have a magnetic moment, in particular the hydrogen nucleus. And that magnetism arises, you can say, because the atomic nucleus is positively charged, but it also has associated with it angular momentum. So you can sort of, in a hand-waving way, view it as being a rotating charge. A rotating charge generates a current, and a current generates a magnetic field. And that magnetic field is, like that of a tiny bar magnet, a magnetic dipole. And the strength of that little magnet, the strength of the magnetic moment, is proportional to the angular momentum, to how fast the nucleus is spinning round. And the constant of proportionality is written as gamma. It's called the magnetogyric ratio, and it's a property of particular nuclei, so it's different for different nuclei. So when we take magnetic nuclei with a magnetic moment in atoms, of course, in matter, and we place that into a magnetic field, quantum mechanics says there are two allowed states of the little magnets. They can point along the field, or they can point against the field. And there's a very small energy difference between those two states. So it's slightly more energetically favourable for the magnets to point along the field, as you would expect from the compass needle. But the difference in energy gets bigger the bigger the magnetic field which the nuclei experience. So the bigger the magnetic field to which the sample is exposed, the bigger the difference in energy. So that is known as the Zeeman effect, and obviously you should mention in this city that was discovered by Peter Zeeman, and he shared the Nobel Prize with Hendrik Lorentz in 1902 for their work in understanding this effect. So at 3 Tesla, which is a sort of magnetic field that we often use for magnetic resonance imaging, the energy difference between these two states is about half a micro electron volt, about half a millionth of electron volt, which is a very small energy compared with the sort of amount of thermal energy that's available at room temperature. So that energy is more like 30 millielectron volts. And so there's lots of thermal energy which is much greater in magnitude than this small energy difference. So it means that at body temperature or room temperature, in a sample which contains many, many atomic nuclei, there are pretty much as many aligned with the field as there are which are anti-aligned with the field, because the energy difference is so small that thermal fluctuations can cause changes in the state. But there is a tiny excess of the number that are along the field compared with the number that are against the field. So if you sort of cancel out those that are up and those that are down, you're left with about 1 in 100,000 extra pointing along the field compared with those pointing against the field. So it's a sort of tiny population difference, but fortunately in matter there are many, many nuclei of interest, and therefore, overall there's enough effect to give you a net magnetisation of the sample. So I'm not sure where the... So you get a net magnetisation of the sample, which is the net effect of all of the nuclear magnets, cancelling those pointing along with those pointing against the field. So that magnetisation is very, very small. So in water at 3 Tesla, 300 Kelvin, it's about 0.01 amps per metre. What does that mean? Well, if you compare that with something like saturated iron, that has a magnetisation of about 2 million amps per metre. So that's a pretty tiny effect. And the effect depends on this expression here. So it depends on the magnetic field that's applied. The stronger the magnetic field, the bigger that slight excess of population is. It depends on the temperature. It depends on the magnetogyric ratio. So it depends on something that's specific to the nucleus. And it depends on the number of atoms per unit volume. So if you want to get a strong magnetisation, you want all of those things on the top to obviously be large. You want a lot of atoms per unit volume, you want a big gamma, and you want to have a high magnetic field. So that net magnetisation, it tends to line up with the field when you place the sample, the object, into a magnetic field. But if somehow you disturb that net magnetisation from alignment with the field, it goes into a precession around the field direction. So it shows a kind of gyroscopic behaviour. So a gyroscope has intrinsic angular momentum. You set the middle part rotating. If you stand it on a stand, it experiences a torque, which tries to make it fall over. But it can't do that because it has to preserve its angular momentum. Angular momentum is conserved, and it can only do that by precessing around the direction of gravity. Well, a sort of similar effect happens with the nuclear magnetisation, because associated with the magnetisation, with the magnetic moment, there is angular momentum. So in the field, there's a torque which tries to realign the magnetisation to the field, but because of the need to conserve angular momentum, you end up with a precession around the field. And the rate of precession, the frequency at which the magnetisation rotates around, depends directly on the strength of the magnetic field and again on the magnetogyric ratio, this intrinsic property of particular nuclear species. So to put some numbers in, to put this into context, for hydrogen nuclei, I should say, at 3 Tesla, the rate of precession is about 128 million cycles per second. So it's 128 megacycles or megahertz, and that's right in the radio wave region of the electromagnetic spectrum, sort of aircraft communication frequency. So it's radio waves which, it turns out, interact strongly with nuclear magnetisation at the kind of fields that we can reasonably well attain. However, whilst we're sitting here today in roughly the Earth's field, which is 50 microtesla, the hydrogen nuclei inside the water molecules in us are all precessing around at about 2 kilohertz frequency. So it's quite a zen thought often just to think about those precessing hydrogen nuclei inside. So the Equilibrium state is the magnetisation aligned with the field, but once the magnetisation is perturbed from alignment, it goes into precession. How do we perturb it from alignment? We do that by applying radio waves. Radio frequency, RF, is applied as a pulse, and that, if the radio waves are tuned to the frequency at which the precession takes place, which is the resonant frequency, then you get a strong interaction and the magnetisation is rotated away from equilibrium, so it's no longer aligned with the field and it goes into precession subsequently. So that resonance, it's a resonance absorption, it's where the resonance, the nuclear magnetic resonance comes from. So if you take a sample and you place that, let's put it into a biological context, take a person, you place them into the strong magnetic field of an MRI scanner, then you get the net alignment of the magnetisation, and then if you then apply an RF pulse to perturb the nuclear magnetisation, you get a precession, and then with the person's permission you wrap a coil around them like so. Then if you then look on the terminals of that coil, you'll pick up an oscillating voltage which oscillates at the frequency of the nuclear magnetisation's precession. So the reason you get that is you get a dynamo effect. So in a dynamo, you have this sort of bicycle dynamo. You end up with a rotation here as a result of the contact with the bicycle wheel, and that rotates a magnet inside a coil, gives you a changing magnetic field. The changing magnetic field induces a voltage in a coil of wire. So that is the signature of the precessing nuclear magnetisation. That's what we detect, that's what we use to make the signal that we use then to make a magnetic resonance image. That signal is proportional to how strong the magnetisation is. The stronger the magnetisation, the bigger the magnet here, the bigger the voltage you get. But it also depends on the rate of rotation. The faster the magnet rotates, the brighter your bike light, the bigger the voltage in this case. So you want to get a big signal, you want to have a big magnetic field, and that then gives you a higher frequency. That's what happened there. So change the magnetic field, make it stronger, the frequency gets higher, but also the amplitude gets bigger as well. So in fact, the voltage you detect is proportional to the number of nuclei per unit volume, the cube of the magnetogyric ratio, and the square of the magnetic field. So you get that because this depends on the magnetogyric ratio and the field, this depends on the field and the magnetogyric ratio squared, and it also depends on how many nuclei you have per unit volume. So to get a strong signal, you want to have a high number of nuclei per unit volume, you want to have a big gamma, and you want to have a high magnetic field. So I mentioned that many atomic nuclei have a magnetic moment, but in fact not all do, and there are some important emissions. So here's just a cut through, I guess, low atomic number nuclei and looking at their magnetic properties. So missing from here are nuclei which don't have a magnetic momentum. Carbon-12 is missing, oxygen-16 is missing. It turns out that nuclei which have equal numbers of neutrons and protons, even numbers of neutrons and protons don't have a magnetic moment. So I'm here looking at this, just picking out a couple of things. So the hydrogen nucleus has a magnetic moment which is written in particular units here, which is about 3, and it has a frequency in 1 Tesla of about 42.6 megahertz, and it's about 99.9% natural abundance of hydrogen, so you get a very strong signal from it. If you compare it with something like carbon-13, that is only 1% abundant naturally, and it has a value of gamma which is about 4 times less than that of the proton, and that means its frequency is about 4 times less. and its sensitivity is about 1/100th of the sensitivity of the hydrogen nucleus because of the reduced gamma, because of the reduced natural abundance. So the situation is that it's actually quite hard. Well, if you want to make images with high resolution, you generally rely on looking at hydrogen nuclei because of their high gamma, and also because there are lots of them around, because in biological systems there's a lot of water present. So the vast majority of MRI is based on measuring signals from hydrogen nuclei in water. That's something to bear in mind. It's not easy to just make an equivalent image with another nucleus which might have an NMR signal from it. You also need to have a high magnetic field, and I guess the story of MRI and NMR has often been a move towards working at higher and higher magnetic field. So this is a sort of maybe a few years old, but it just shows a plot of the magnetic field that's accessible versus the size of the aperture of the magnet along this direction. And this is the sort of leading edge where you can get to very high fields if you're prepared to have small samples inside a sort of a small bore magnet, 22 Tesla at this time. Whereas if you want to look at human subjects, then, well, the maximum fields are around about 9 to 10 Tesla, but the operational range, most clinical scanners are working at 3 or 1.5 Tesla. So most MRI is done looking at the signal from hydrogen nuclei in water at fields of greater than or equal to 1.5 Tesla, because that gives you a strong signal. Okay, so the overall evolution of the magnetisation, how once you've excited that equilibrium magnetisation from being aligned with the field, how it then progresses over time, is described by a set of equations called the Bloch equations, named after Felix Bloch. So I'm not going to go into all the detail of those, I don't think it's appropriate, but I want to point out that it have introduced two new quantities here, which are times, written as T1 and T2, and this time T1 is sort of linked to the magnetisation that's along the direction of the field, which we call the longitudinal magnetisation, and this time is linked to the magnetisation which is perpendicular to the field. We're going to look at their effects in the next few slides. So one way of looking at what happens over time when you perturb the nuclear magnetisation with a radio frequency pulse is to draw the magnetisation as an arrow and then follow where the arrow moves. So it's an arrow because magnetisation is a vector quantity. It has a direction and it also has a strength. So when you excite the magnetisation, well, at equilibrium you end up with the magnetisation along the field direction, which by convention is Z, vertical in this case. You rotate the magnetisation with an RF pulse into what we call the transverse plane, so it's perpendicular to the applied field. And then what happens is it precesses around the direction of the field, and it goes round very rapidly. It goes round at, if we're working at 3 Tesla with protons, hydrogen nuclei, it's going round at 128 million cycles per second. So every 8 nanoseconds there's a rotation around. So it's kind of hard to get your brain around what's going on with the magnetisation that's going round at this massive rate. So what we tend to do is we imagine ourselves in a frame of reference which is also rotating around at 128 million times per second. So then we're going round with this arrow and it stays stationary. So if anyone remembers an old record player, LP player, it's sort of like you're standing on the LP player and going round with it, going round with the record, as opposed to standing aside and watching it going round. So it just simplifies analysis of the evolution. We don't have to worry what's happening every 8 nanoseconds. We can think about what's happening over a bit of a longer time scale. So that's called going into the rotating frame of reference. And in that frame of reference we can take a sort of longer look of what's going on. And what happens is we start to see the effect of the NMR relaxation. So what happens is this component of the magnetisation decreases and this one starts to recover. So we go from a situation where we have only the magnetisation that's processing around, now stationary because we're in the rotating frame, to something where the longitudinal magnetisation gradually grows and the transverse magnetisation gradually decreases. And we end up eventually back at equilibrium where we started. So if we track the strength of those components of the magnetisation over time, what we see is that the transverse magnetisation decays exponentially with a time constant T2, and the longitudinal magnetisation recovers exponentially with a time constant which is written as T1. That's called T1 recovery, going back to equilibrium. That's T2 decay, because the magnetisation is decaying to zero. And I gave the game away there. The signal strength we see depends on how much magnetisation is processing around at 128 megacycles. And so that depends on the amount of magnetisation on here, which is decaying away, like so. So our signal would also decay away with the time constant T2. So that dictates how long the signal will actually last for. So the sort of timescales, the characteristic timescales when we're thinking about water in biological systems for these processes are between 10 milliseconds and maybe 10 seconds. Those times, they're sensitive to lots of different things, and that's actually pretty good because it gives us sensitivity to NMR, which can be translated into MRI and give us contrast in images. So we can sensitize the measured NMR signal to reflect both of these effects. We can make the signal strength depend on this curve or on this curve or on both of them, in fact. So how do these times vary, or what do they depend on? They depend on, as I said, lots of different things. They're driven really by fluctuations in the magnetic fields which are experienced by individual nuclei. And those fluctuations are driven by molecular motion, and they're also affected by the strength of local sources of magnetic field. So two different things. Molecular motion is important, and sources of local magnetic field both affect the relaxation times. But just thinking about the molecular motion effects, this is the kind of common plot that people show, showing the variation of the relaxation times, T1 and T2, as a function of the correlation time of the motion. So if you have a slow motion, a motion which is slow, I should say, then the correlation time is long, whereas a fast motion has a short correlation time. So sort of larger molecules will tend to have longer correlation times, increasing restrictions on motion when we're thinking about water molecules due to binding or being sort of surrounded by macromolecules will tend to move us to having a longer correlation time. So the two relaxation times actually show slightly different behaviour. They both get long as you go to very short correlation times, lots and lots of movement. But as you go towards more solid light structures, T2 decreases and T1 starts going back up again. So there's a definite minimum of T1, but T2 in solids gets very short, T1 gets long. So those behaviours give rise to variations of these quantities depending on the molecular environment of the water, and that's important because in tissue the environment can be quite significantly different, and therefore these relaxation times can be different and are different in tissues. So we often interchangeably talk about R1 and R2, they're just rates as opposed to time, so R1 is 1 over T1, R2 is 1 over T2, and in the context of this meeting, R1 and R2 are generally increased by presence of iron and myelin. So related in iron, there's a source, well, as we'll come to see, I'm sure you know, there's a source of magnetic perturbation when you have iron around because it has strong magnetic properties. In the case of myelin, there are also magnetic field perturbations. There's also potentially binding going on, and perhaps it's less clear exactly what the underlying effects, the main sources of myelin's effects on iron and R2 are. And so that means just obviously T1 and T2 are reduced by the presence of iron and myelin. So here's an example of a nice image acquired at 7 Tesla, which has been acquired in a way to make it sensitive to T1 relaxation. And you can see that by doing that, you get really nice differentiation of the grey and white matter of the brain. Very different intensities for the grey and white matter. The white matter tends to have a shorter T1 relaxation time because of the presence of myelin, and therefore, like in this context, it ends up with a larger signal occurring. And you can really see the boundary pretty clearly between those two different tissues in this particular image. So just one other point to mention, which will then come up later on, is that we've gone through this process of saying we'll go into the rotating frame. We do that by going round at the rate of nuclear precession, which is given by gamma times B0, which I said was like 128 megahertz. But the fact is that in a real sample, a heterogeneous object, the magnetic field actually varies a little bit between different regions and between different tissues. And also, when we're making images or any measurements with NMR, we might want to vary the magnetic field in different regions of the object by an amount which isn't this big. This is pretty big, say 3 Tesla. We might be varying it by, a millitesla or so, or less than that. But we need to think about what the effect of making that variation is. So we said we go to a rotating frame by standing on the record player, going round at 128 million times a second, and then if our nuclear magnetisation is also going around at the same rate, it would stay stationary. But if there's a small additional field, then the magnetisation actually carries on processing around in that frame. So it's sort of going a little bit faster than the frame we've chosen to be in. And therefore there is a net movement of the magnetisation in that frame of reference, but it's much slower. It might be 100,000 cycles per second, it might be 100 cycles per second. It's a much lower frequency range, but it's quite an important effect because it's that effect we use to encode position in MRI. So that's something we have to think about. So one thing we can think about when we analyse that movement is what is the angle this vector makes with one axis. We could say the x-axis in this rotating frame. And that angle is going to increase with time because it's just a linear movement, a rotation at a constant angular velocity of that vector. So that angle we call the phase. It's a phase angle, and that's something that we'll come back to look at later on. And if we look at the signal that's made by that precession at this lower frequency, what we'll see is an oscillation like this, and it would decay with time in this case because of T2 effects. So the NMR signal we see is a decaying oscillation. The oscillation depends on the offset of the frequency from resonance, essentially. So what I haven't described is sort of what we do is when we measure a signal from the sample, it's at 128 megahertz. What we actually do is we demodulate the signal. We take out the 128 megahertz frequency and we look at the difference from that. And that's equivalent to this operation of going to a rotating frame and then looking at the evolution of things that are moving at slightly different frequencies from 128 megahertz. So the rate of phase evolution with time, which is this, tells us about the field offset. And that's important if you want to use information about frequency offsets to tell us about field effects. Okay, so I did put in some sort of recaps into these things. I tried to condense everything into one sentence, bites, so it's probably worth just recapping. So many atomic nuclei have a magnetic moment. These collectively show a weakness alignment with the applied field, and they show precession when they're disturbed from alignment. They can be excited into precession by tuned radio frequency. The NMR signal is produced by electromagnetic induction. The vast majority of MRI is based on water. We like to go to high field because that increases the signal strength, makes magnets more expensive, but it's worthwhile generally. T1 and T2 relaxation returns the sample to equilibrium, and T1 and T2 relaxation is sensitive to local ion and myelin. Okay, so that's all of MRI, all of NMR. Let's now do all of MRI. So, magnetic field gradients are at the heart of magnetic resonance imaging. So, a magnetic field gradient is a linear variation of the magnetic field with position. So, it's a magnetic field, which in this case I'm showing the variation in just one direction, in the x direction. So, the magnetic field is a linear function of x, and the rate of variation is g, which is the gradient strength. So because we know that omega, the frequency of precession, is equal to the magnetogyric ratio times the field, it means that in this situation, if we apply a magnetic field that varies linearly with position, then the NMR frequency also varies linearly with position in the object. So we take two different positions along this axis, then we're going to get two different frequencies of the signal because the field is different at those two different locations. So we can distinguish the signals coming from these two different locations because the signals occur at different frequencies. So the measurement of the NMR frequency indicates position. So that's really what underlies magnetic resonance imaging. It's the use of a magnetic field gradient, so you apply additional field that's varying with position, and then you measure the frequency of the signal, and that tells you where the signal is coming from. And that was the idea that Paul Lauterbach had and Peter Mansfield in the 1970s. So just to take it a little bit further, let's consider a very simple object, two-dimensional object, to make life easier. We're just going to get signal from this region and signal from this region. To put it in its proper biological context, we get signal from the two eyes there. And they're at different positions, so we get signals occurring at different frequencies. And the way I've set this up, then, the two signals have different frequencies, but they also have different amplitudes because this box is smaller than that box, and so there's less nuclear magnetization, less hydrogen nuclei, less water molecules inside here compared with here, and therefore the signal we get from here is smaller. So the signal amplitude tells us how much stuff there is in the location. The signal frequency tells us where the location is. So the actual signal we detect, if we make a measurement, is just the sum of these two signals, which looks a bit more complicated, a little less easy to interpret, but actually decomposing signals into their constituent frequencies is something that there are very good mathematical techniques for doing. The Fourier transform is the approach that's used. So you take a signal, you Fourier transform it, and you end up with a measurement of how much signal is occurring at each different frequency. And then, because of the linear relationship between frequency and position in the presence of the gradient, you can then say how much stuff there is at each different position along the x direction in the object. So that's what you can do. In a more complicated object, then you don't have just two signals, you have to sum the signals coming from all the different x positions across the object to work out how much signal will occur at each frequency. That's what's shown over there. So you'd expect to have a reasonable amount of signal here, much more signal here because you've got a wider extent, and then if you go over to this side, you'd expect to have less signal occurring. So the signal you get gives a less obvious immediate signature of what's going on in the object, but in the same way as before, if you apply a Fourier transform and you decompose that signal into its constituent frequencies, you end up with something which tells you about how much signal is coming from each different location along the x direction across the object, and that would look something like this. You'd expect it to be quite big here, but bigger here because there's more stuff at that particular x location. So you can call this a projection of the object. It's like sort of projecting down all of the signal, projecting down, counting all of the hydrogen nuclei down this direction at each x location, and then plotting out that value here. So actually that was the way that people came to imaging in the first case. So Paul Lauterber's paper in Nature 45 years ago, which described the first imaging experiments, what he did to make the image was actually to make those sort of projections like I just described, but with the gradient applied at different angles. So like viewing his object was a very simple one with 2 tubes of water inside a holder made of material that didn't generate any signal, and then by applying gradients at different directions he was able to measure projections of the object from different directions, and then you can combine those with a technique which was used at that time for CT, X-ray tomography. You can make an image like this. So I'm using that example, but it's fair to say it's not really how people generate images nowadays. Projection reconstruction imaging is used in some circumstances, but it's not the main technique. But it has within it, hopefully it captures some of the important concepts, which are to make an image you have to make multiple measurements usually. You can't do it with just a single measurement, and you generally have to change the gradients that you apply in order to encode information in more than one spatial dimension. So in this case, he made multiple measurements with the gradient along different directions, and so multiple signal acquisitions, different gradients. So I'm not going to go into the detail of the way in which images are generated now. You can have whole conferences on that topic really, or just understanding the acronyms you can have conferences on. So, but just the general features of an image acquisition are that you will excite a signal with a radio frequency pulse, and then you'll apply some gradients to encode spatial information. Thank you very much. So you generate a signal, and then you'll measure that signal, but you'll choose often the time at which you measure the signal. So there's an important parameter in imaging which is called the echo time. So it's the time at which you measure the dominant components of the signal. And I'm obviously not hiding something, there is an echo in there, but I'm not going to try and explain where the echo comes from. But we measure a signal at a particular time, and that's an important parameter in the imaging sequence. And also, we have to make repeated measurements. So we repeat the process, and we leave a time which is written as TR, the repetition time, between successive measurements. And that's also an important time because it dictates lots of things about the imaging sequence. Let's pick out 3 things that are important. So firstly, those times control to quite a significant extent the contrast in the image, the appearance of the image, because the image intensity will depend on the amount of the signal is decayed away through T2 effects before we make the measurement at the echo time, and it will also depend on how much signal has recovered, how much longitudinal magnetization has recovered between successive measurements. So these 2 things by varying the echo time and the repetition time, we can change the way the image appears almost completely. So the TE, the echo time, controls the T2 star contrast. So if we increase the echo time, we get more sensitivity to signal decay, because we've allowed longer for that. So just showing that effect, imagining we have 3 different sources of signal which are decaying at different rates. So actually white matter, grey matter and cerebral spinal fluid. Then if we were to make a measurement with a very short echo time over here, all of these signals would be a similar strength and we wouldn't get much contrast between the different tissues in our image. Whereas if we make a measurement over here where these tissue signals have decayed quite a lot, we can end up with contrast in the image. TR controls the T1 contrast, as I said, and reducing TR increases the T1 contrast. So this is the recovery back to equilibrium, again for those tissues. Recovery happens fastest for white matter, next fastest for grey matter, slowest for CSF. And again, if you make a measurement at a short TR value, then there's quite big relative differences here. We'll get good contrast in the image, whereas if we make an image over here, we'll get less contrast, certainly between the grey and white matter in the image. So we can control the contrast in images by varying those very simple imaging parameters. So here's just an example of this. 2 images obtained at 1.5 Tesla in sagittal images in the brain, and this is where we have a short echo time and a short TR relative, so we end up with T1 contrast. So the white matter of the corpus callosum appears bright, it's got a short T1, whereas the CSF, which has a very long T1, appears dark here. Whereas over here we get T2 contrast by making TR quite long and making the echo time quite long as well. So the signal's decayed away, and now the signal from the CSF is very strong because that decays very slowly in the sort of water-like tissue. So just the feeling that you can control the contrast, you can make images look very different by varying the imaging parameters. That's a great strength of MRI. It's also, I guess, a complication because it means that there are many different ways images appear. You have to specify very clearly the way in which the image was acquired in order to understand or interpret what it's going to show you. Just a bit about image resolution. It turns out, without going to depth, the resolution that you obtain depends on the inverse of the gradient strength and the inverse of the time that you measure the signal for in an individual acquisition. So to get high resolution, you'd like to have strong gradients and you'd like to acquire the signal for a long time. But the signal decays away, so there's a limit on how long you can acquire it for. You can't keep acquiring it forever, it will be gone, so that's a limit. And there's also a limit on how strong gradients, the gradients you can make can actually be. Perhaps more importantly, the nuclear magnetic resonance and magnetic resonance imaging is a relatively low signal strength technique. And it's often it's the signal to noise ratio which often kills you when you try to go to higher and higher resolution. Because if you think about it, the signal to noise ratio scales as the cube of the size of a voxel, the size of a region, a little cubic element usually that gives you the signal that you put at a particular point in the image. So if you scale the size of the voxel dimension by a factor of 2, then the volume goes down by 1/8, and therefore the signal decreases by a factor of 8. So as you try and increase the resolution, you lose signal to noise very quickly. So resolution is usually limited by image signal to noise ratio. You can increase the signal to noise ratio by averaging, by acquiring the signal lots and lots and lots of times. But obviously, that scales fairly slowly with the number of acquisitions you make. And so you have to work pretty hard to overcome a reduction like this. You have to acquire 64 times as many averages to do that, and that takes time and things get long, people get uncomfortable inside the scanner usually. So I guess it's a sort of, order of magnitude type of resolution we can get to nowadays. So maybe 0.5 millimetre isotropic voxels for structural brain imaging at 7 Tesla, 1 millimetre-ish for functional brain imaging, 0.1 millimetre for post-mortem brain samples at 70 when you can leave them in there for a very, very long time, and maybe 10 microns in a microscope system with a very small sample. So we're not going to be imaging individual ferritin, so it's not going to really happen unless we use other methods for detecting nuclear magnetic resonance. And there's some of those on the horizon, but they're not really going to probably be impacting on imaging live human systems, human people. Just a bit on the imaging time. So to make a two-dimensional image with n by n voxels, so n voxels along this side, n along that side, it takes round about n times TR to make that image. If you want to make a three-dimensional image, which we often do, which is going to have n cubed voxels, then it takes about n squared times TR to make the image. But we've seen that in order to allow the signal the magnetisation to recover, to give us a reasonable signal, then we need to have a reasonable time for T1 recovery to occur. So in a sort of hand-waving way, the acquisition time is going to scale roughly as n times T1 and n squared times T1. And given T1 can be seconds, then we're talking about quite long acquisition times. Fortunately, you can quite aggressively scale these things down. You can get more information for every acquisition. You can actually make TR quite a lot less than T1, but you pay for that in signal-to-noise ratio. But I guess the point to make is that the imaging time is always going to be limited to some extent, and there's a compromise between signal-to-noise ratio and imaging time. The longer you can acquire for, the better the signal-to-noise ratio is. So I guess again, sort of ballpark figures, the minimum time is really about 10 milliseconds maybe for a two-dimensional image. The typical time, perhaps a second. The minimum time for a 3D image, being optimistic, is about 100 milliseconds. The typical time is sort of minutes. So these are the sort of time scales we're talking about for acquiring magnetic resonance images. I'll very quickly mention just what goes into an MR scanner. Essentially, you can view it, a common system, as a set of concentric coils. You have big coils to make the magnetic field. They're usually superconducting coils, and so they carry the current forever and ever, and they make a very strong, stable magnetic field. These are sort of typical commercial systems, and then if you take off the covers, you see what's underneath. Basically a vacuum flask containing liquid helium, keeping the windings cool. If you go to preclinical systems, you can go to higher field. If you go to vertical systems, you can go to even higher fields. And there are some systems around where we'd hope to image human subjects at fields of very, very high fields, like 12 Tesla. This is a system that's just gone into neurospin in Marseille. I think he's not up at field yet, but it's an exciting prospect. I think I'll just skip the other coils and move on to a sort of recap. So magnetic field gradients spatially resolve the NMR signal. Fourier transforms used to identify frequency components. T is the echo time, dictates the T2 contrast. TR is the repetition time, dictates the T1 contrast. Spatial resolution is limited by signal-to-noise ratio. The imaging speed is limited by signal-to-noise ratio. And, well, the MR scanner is a nested set of coils, essentially, an expensive nested set of coils. Okay, so that's MRI. Now, onto magnetic fields. So, magnetic fields arise from electric currents, essentially. So we can work out the magnetic field that a little element of current makes with a nice equation by a Savart law. And if we know where the current is flowing in our magnet, we can make a very accurate assessment of all the magnetic fields that are being produced. But the problem comes when we place the subject inside the scanner, because inconveniently the subject is made of matter, and all matter has magnetic properties. And that gives rise to magnetisation. So I said that the nuclear magnetisation is generated when we place the subject into a scanner, but there's actually a stronger magnetisation which is more important for dictating the magnetic fields, which arises from actually the electrons in the matter. So the quantity that's important often for understanding this is the magnetic susceptibility, which is written as chi, and it's the thing which really characterises the magnetic properties of matter. It relates the magnetisation to the applied magnetic field. So in many materials, the magnetisation is just proportional to the applied field, and the constant of proportionality is the magnetic susceptibility. So that's the thing which is the property of different tissues. So we should remember the magnetisation is a vector, and it's generally, in these simple systems, parallel to the applied magnetic field. So the magnetisation depends on the field via this constant proportionality. The thing we're interested in for NMR and MRI is the B field, which dictates the NMR resonant frequency, and that also depends on the susceptibility. So it's going to affect the NMR signals that we measure. Now, susceptibility can be negative or positive. So negative corresponds to diamagnetic materials, positive corresponds to paramagnetic or ferromagnetic materials. So we take a uniform magnetic field in vacuo, and then we place into it a material which is diamagnetic, so has a susceptibility less than 0, negative susceptibility. It acts to try and expel the magnetic field, so it reduces the magnetic field inside the material. Whereas a paramagnetic or ferromagnetic material attracts the field lines and acts to enhance the magnetic field inside it. So when we're talking about biological systems, diamagnetic materials generally have, well, they always have negative susceptibility values which are quite small. So for water, it's about -9 parts per million. Fat, maybe -8 parts per million. Bone, -11 parts per million. So parts per million means times 1/1,000,000, essentially. So these are small effects. In the biological context, paramagnetic materials always have positive susceptibility values. In the biological context, they contain constituents with a net magnetic moment, often iron-bearing compounds. Ferromagnetic materials have large positive susceptibility values, and they obviously retain magnetisation even in the absence of an applied field. And we tend to keep them away from MRI scanners because they get drawn into the scanner and become dangerous. So when you're dealing with susceptibility, it's worth bearing in mind that it's quite a confusing literature sometimes, because there are different kinds of susceptibility. The one I was just talking about is the susceptibility per unit of volume, but you can also define a susceptibility per unit of, per mass unit, which you get by dividing the volume susceptibility by the density, and you can get the molar susceptibility of a mole of material. And to add things, make things even more complicated, susceptibility values are still often quoted in CGS units rather than SI values. So one useful thing is to convert susceptibility from CGS to SI multiplied by 4 pi. And you can remember that, you can always convert between the two kinds of units relatively easily. So just for water at 293 degrees Kelvin, in SI units the susceptibility is -9. But in CGS, it's 0.72 because you divide it by 4 pi. The mass susceptibility, you have to divide by 1,000, so you get -9 times 10 to the -9. Here you're dividing by 1, and so you get a different value. So you can see how to convert between these different kinds of units relatively straightforwardly, but it just can be a bit confusing sometimes. And people, ideally, I think, should use SI units. I don't know, that's my feeling anyway, from now on. So a bit on paramagnetism. So paramagnetism arises in materials which have atoms or molecules which have a net magnetic moment. So in the same way that we looked at with thinking about nuclear magnetic moments, they can line up parallel or anti-parallel to the applied field. So as you apply a field, you get a net alignment of the magnetic moments, which gives you a net magnetisation, which contributes to the susceptibility. But these magnetic moments are generally, when we're talking about electron effects, they're much bigger than the nuclear magnetic moments, and therefore you can get quite strong magnetisation through this effect. And eventually you can get to the situation where all of the magnetic moments are lined up with the field, and then you've got saturation. So the signature of this effect is that eventually it will saturate at a high enough field, and it's producing a magnetisation which is positive, so along the field direction. And it's much bigger than the effects that I talked about right at the start of nuclei, because the magnetic moment of the electron is much bigger. It's about 2,000 times bigger than the magnetic moment of the nucleus, typical nucleus. So we can sort of forget the nuclear magnetisation when we're thinking about the effects of matter on the magnetic fields generally in a sample, in an MRI scanner. Diamagnetism arises from the tendency of movable electrical charges to partially shield the interior of a body from an applied field. So it's Lenz's law tells you if you move a magnetic field around a coil, you'll induce a current which will produce a field that opposes the field change. So in a hand-waving way, the electron orbitals will be distorted to oppose the field change. So the interesting thing with this effect is that it just keeps going, getting bigger and bigger. It doesn't scale with, it doesn't saturate out as you go to higher and higher fields. So it's a magnetisation which is opposite in direction to the applied field, and it just keeps getting more and more negative. The diamagnetic effects get stronger and stronger as you increase the field. They don't saturate out. So all matter generally manifests this diamagnetism, but in systems which have paramagnetic atoms or molecules inside, the diamagnetism is usually swamped out, and because the paramagnetic effects are stronger. Ferromagnetism results from really coherent collective effects where you end up with net alignment of the majority of the magnetic moments of systems. So usually in a solid system, alignment on a lattice gives you a strong magnetisation. You can also have ferrimagnetism, where you have maybe different sites on a lattice with different strengths of magnetic moment atoms on the different sites, and that gives rise to similar sorts of effects but a bit weaker in magnitude. So I mention that because obviously iron we know is ferromagnetic, hematite, rust is also ferromagnetic, whereas another oxide of iron, magnetite, is ferrimagnetic. So these effects, they're not so important as far as we know so far for MRI, but there's an interesting issue with things like magnetite. Are they making some contribution to what's going on? And they have been used as contrast agents in the past. So in general, on the spectrum of magnetic susceptibility, then you have a huge range, but biological samples are sort of in this mid-range, around about 0 essentially. So in the range that I mentioned before, so with a lot of iron, you might move the susceptibility towards a more positive value than 0, but it's very hard because the water has such a strong negative effect on the susceptibility. So here's a look more closely at different things that maybe are biologically important in their susceptibilities. So oxygen is paramagnetic, air is very weakly paramagnetic. Then most tissues around about -9 parts per million. So things that move us away from the -9 parts per million of water are increasing density, maybe makes things more diamagnetic, so bone, for example, whereas adding iron or decreasing the density tends to make us more paramagnetic in what we see. So the largest effects actually of susceptibility in magnetic resonance imaging are from air tissue boundaries, because there you have a big difference in magnetic susceptibility, about 9 parts per million. The effects of variations of iron content and other things are a bit more subtle generally. So the presence of paramagnetic material, particularly iron, increases the susceptibility. Denser materials such as bone are generally more diamagnetic than water. So the effect of water's magnetisation is very, very small, but it is actually big enough to produce levitation. If you apply a big enough gradient of the square of the field, you can produce a force which will balance out gravity, and you can levitate watery objects, as was done in Nijmegen in these experiments with various different samples. Just a couple of things to finish off. So just mention, one example where iron has a significant effect is in hemoglobin. So the magnetic state of hemoglobin changes significantly depending on whether it's oxygenated or deoxygenated. So deoxyhemoglobin is paramagnetic, but oxyhemoglobin is weakly diamagnetic. And it's the change of the susceptibility between the venous side and the arterial side which gives rise to quite a lot of contrast in magnetic resonance images, and it's also that change of the blood susceptibility with changes in oxygenation which underlies the BOLD effect, the blood oxygenation level dependent signal effect, which is exploited in fMRI experiments. So hemoglobin, iron there is having a significant effect. So recapping on this, magnetic susceptibility relates to the field to magnetisation, can be positive or negative, all materials are diamagnetic. Para and ferromagnetism, when atoms and molecules have magnetic moments. Most tissues are weakly diamagnetic because they're watery, but iron in tissues increases the susceptibility. So I have a few more, I'll go through these, I just pick out a few points. So why is that important? I'd just like to get to that point. Because it's important because the magnetic field in a heterogeneous object depends on the boundaries between regions of different susceptibility. And the variation of magnetic field that produces affects the NMR frequency and therefore affects the way the images appear. So Maxwell tells us that when we work out what the field variation must be inside a heterogeneous object, then the magnetic field B has to be continuous across the normal of the boundary, and H has to be continuous at the tangent to the boundary. Why is that important? It means that the shape of the boundary affects the magnetic field pattern that's produced. So you can get a bit of insight by looking at some very simple shapes. So I'm not going to try and explain it, but for the people who are aware, sphere of Lorentz, should mention that in the Lorentz Centre. We're using the sphere of Lorentz in this for those who are aware. So if you take a sphere of material of some susceptibility, you place it in a magnetic field and you work out the field perturbation that generates, you get zero offset inside the sphere and you get a spatially varying field outside the sphere. What does that look like? Looks like that. Uniform field inside, spatially varying field outside. If you do the same thing for a cylinder which is perpendicular to the field, same thing happens. Uniform field inside, spatially varying field outside. Why is that important? It's important because it dictates the way the signal evolves from the whole sample. So taking the case of the sphere, if we look at the signal from this region here, which experiences a positive field offset, that will evolve in the rotating frame in a particular sense, whereas the field from the signal from over here, which experiences a negative field, evolves in the opposite direction. It experiences a lower precession frequency, whereas something over here, which experiences no offset, just stays stationary in the rotating frame. So as time progresses, that effect increases, and when you add up the contributions of all these different signals, they'll tend to cancel each other out. So this, the element of this arrow pointing this way cancels the element of the arrow pointing that way. And so the signal reduces as a result of the effect of the field inhomogeneity. So you end up with an average signal which will decrease quite quickly over time, and also we end up with a signal whose average phase depends on the average field which this object produces. So a signal might look like that, has a frequency which depends on the average field, and it decays at a rate which depends on the overall inhomogeneity that's present. So the important point is the heterogeneous susceptibility affects the signal evolution quite significantly. So we can see that manifested in this image here particularly, which has been acquired so to be sensitive to T2 decay quickly. So if we look into a region of the brain, comparing it to a T1 weighted image, we see clearly small venules in the small veins, primary cortical veins in the grey matter get picked out very clearly because of the field inhomogeneity around the veins, whereas we don't really see that in a T1 weighted image. And if we look at the phase of the image in a slightly processed fashion, we also see a significant effect of the phase of the signal of the hemoglobin. So we've got two things which give us a signature of the magnetic properties of the tissue. More fundamentally, we can look at those across, not just around a venule, we can look at those field variations in the whole brain. We can look at the decay rate of the signal in the whole brain, and it reveals things which tell us about the magnetic effects of myelin in the tracts, increasing the relaxation rate, iron in the deep grade nuclei, increasing the relaxation rate, myelin reducing the average magnetic field, and not so obviously, on average, an increase in the magnetic field from the effect of iron in the deep grey matter. And as hopefully others will tell you about later in the meeting, you can use that information to actually map the magnetic susceptibility. It's an exciting development over recent times. So apologies, I've gone over time. I won't read through these, but I should say, hopefully I've given you some flavour in a rather rapid canter through NMR, MRI and magnetism, but hopefully poses some interesting ideas that people will pick up later on in the meeting. Thank you for bearing with me.